I think last time we ended up with pitfalls and analogies. I think we covered heating and cooling. Pitfalls and analogies. Basically, let's go ahead and do the animated slideshow. Current slide. Maybe I'll have myself some, I want a highlighter, and then I want my color. Oh, pointer options. Light color to my highlighter. Let's try light. See what that looks like. Anyway, small scale, easy. Easy to design, easy to operate. Limitations are not nearly apparent. Large scale limitations become obvious and significant. The inability to scale up shows, and the failure of pilot plant studies show. And you have failure to commercialize, basically. And in the technology transfer area, there exists some human attitudes, right? NIH, not invented here, right? People have an attitude that if we didn't think about it, then it's not worth worrying about. You also have people working in a box. Now, that's tough. You also have poor communications. That's tough. And you have definite lack of information. Now, these are serious problems, right? And we'll toss in the concept of expert here for a second. You got all kinds of experts out there. I quit being an expert professionally because I was more of a student rather than an expert. I was constantly learning stuff. So what happens if you have two experts together, they never really seem to agree. They're arguing, okay? And if they argue and disagree, means that one of them's wrong, or at least one of them's wrong. Both of them could be wrong. And my suggestion is, if one of them's wrong, why are they called experts? So this human aspect of scale-up is quite interesting. Can lead to very serious problems. Anyway, some of the other problems, major pitfalls. MP is major pitfalls. Unrealistic expectations are common, and these lead to very expensive mistakes, right? Insufficient knowledge is commonplace. Numerous examples. Complexity of the phenomena, complexity of fluid mechanics. Example, when you put power into a gas sparge system, two sources of power. One is from sparging itself, and one is from mechanical agitation. Hydrodynamics is quite complicated. Gas-liquid circulation. In other words, the idea is I have an impeller in here and it's dispersing gas. How much of that gas goes to the top and how much of that gas gets recirculated in? If it's recirculated in, it's in a sense old gas, and it dilutes down the concentration of the new gas coming in. And also, mass transfer correlations do not include all kinds of items, coalescence being one of them. Surface charge, electrical charges being another. Anyway, so things are complex. That's the whole idea. It's a very complex environment. Some process objectives are incompatible. Basically, they can't be met, right? Procedures and operations available in the laboratory are not available in the pilot plant. And some of these are obvious. An example is shaking tables, right? You can shake laboratory equipment. You can have a shaker table with beakers on it, right? You have a beaker here, and then over here you have a beaker. And you can do your studies in beakers and on a shaker table. You don't have that in the pilot plant. So that's an example of something that's basically non-scalable. It's the idea of scalability. Some systems are not scalable. They don't lend themselves to scaling. To be asked to scale a non-scalable system is painful for everybody involved. Some processes cannot be scaled to larger sizes for technical reasons. One of them is the phenomenon doesn't happen on a large scale. Right. An example is if the chemist has to break the beaker to remove the product, or break the test tube to remove the product, that scale-up is not going to be easy. If the reaction yielded a sticky product which accumulated on the impeller, the reactor in the lab, they just shook it to remove the products, but you can't shake a 10,000-gallon reactor in the plant. You may perhaps jostle the impeller a little bit, but whether that lets the material come off the impeller, I'm not sure. Scale up of a splashing regime, shaker tables, is not necessarily possible. Although I would like to enjoy doing that sort of challenge to see if you can scale up from shaker tables to an agitated tank. All right. That would be quite an interesting scale up question. You can't have a 10,000-gallon shaker. Some phenomena cannot be scaled since the phenomena doesn't exist. The zeta potential is an example. Right. Zeta potential measures, I think, the voltage across the double layer. So the double layer, you have a lot of pluses here, and the pluses attract minuses, so that's the double layer. This being a surface. That potential voltage drop across the double layer is not scalable because often the flow regime changes and there is no double layer. You have a flow coming in, removing the charges and carrying them off. In a highly turbulent flow, there's a lot of surface renewal going on, and a double layer is much more difficult to form. Difficult scale, retreat blade and unbaffled tanks. Basically, I'd have to say that it's difficult to scale. You take this Fodler design, looks like chicken legs, right? It's made of glass, and it has maybe a baffle in here, beaver baffle, or an H baffle. H looks like that, I guess. Now, the reason why this impeller is difficult to scale, by the way, this impeller is used everywhere in the pharmaceutical industry. So it's 50%, its use in pharmaceuticals is about 50%. So it's a very popular design, primarily for two reasons. One, it's glass, and two, glass is inert, not participate in the reaction. And also, it has a very large D over T ratio, D over T ratio of 0.7. That makes it very effective at mixing. Very effective large diameter impeller. The problem is the flow behavior in this tank is a function of fill height. Okay, if I'm going to fill it all the way up, where the height is equal to the diameter, okay, that you have the beaver baffle or the H baffle in there. That's one set of behaviors. However, if it's low volume, what happens is the material gets sped up along the sidewalls, and that's another type of flow behavior. So you have a lot of changes going on as I raise the liquid level in this tank, and those changes will give rise to differences in performance. So we call that, might be considered a central vortex, and the inability to predict the vortex or the effect of liquid height on the vortex. See, with the vortex going through the impeller, you're going to have a lot of surface entrainment going on. A lot of probable poor mixing. Up here at the top, you'll probably have very good mixing. Anyway, so you may run into difficulties in certain designs because the flow regime changes with volume or quantity or the hold-up volume. Right. Remember, going back to our n theta, the number of revolutions to mix, it was a function of volume, right? We have volume, and n theta will go up as volume. Other systems that perhaps will lead to difficulties in scale up. So in laminar mixing, the viscosity is important. So you can anticipate large viscosity differences in laminar mixing may be difficult to scale. Similarly, mixing with large density differences. Density is important in turbulent flow. As a result, large density differences may be difficult to scale up. Systems that are stratified are probably going to be difficult to scale up. And systems with have poor mixing is going to be difficult to scale up. So those are some of the items that cause difficulties to scale. And we have our old buddy, the transition regime, right? Causes and effects are poorly understood, data is contradictory, parameters are unknown, variations occur, and operating problems occur. Remember, the n theta value during the transition regime went up like that. A transition bump, right? So it does not operate in the transition regime because of unpredictable results. Here you're having a rising, here you're having a falling relationship. Generally, it's unfortunate the transition region occurs because processes are forced to operate there. And typically the transition range is from 1,000 in Reynolds number, or maybe even 300 in Reynolds number, all the way up to 5,000 in Reynolds number, right? So, transition regime, that's essentially also the flow regime changes here. Liquid height, right? Center vortex forms at low liquid levels. At high liquid levels, there is no vortex formed. You have a difference in flow regimes, differences occurring here. At low fill volumes, it may be very poor mixing because you have a tendency to have solid body rotation. And this is typical. You rarely have a full process description. Rarely do you have a full process description. Processes are variable. They're very complex. Lots of not known. And some processes are unpredictable a priori. So, lack of a complete pilot plan study. Oh, yes. No matter how long you study something, it's going to be incomplete. There's always more questions to be asked. And if you're studying, you usually don't have hindsight. Time limitations exist. Similarity parameters are not identified. Left incomplete for lots and lots of reasons. Lack of important process information. Simple information is often overlooked. How long did it take to add the feed? Where did the feed go once it entered the vessel or the equipment? Where was the reaction taking place? How long did the reaction take? What's the difference between the mixing time and the reaction time? So, lack of experimental information, reaction times and transport times or mixing times. How long did it take to add the material? Simple questions. How long did the reaction take? What was the dissolution rate? So we have a very dangerous situation here. What a large-scale process is doing has not been documented on a small scale. That's an interesting statement. What the process will do on scale up may not be known. That's another reverse. So you have a situation like that. Less severe pitfalls. These won't necessarily prevent translation, but process scale up. That's translation is process scale up. Translation may be less successful. Maybe it's less successful because of these. Optimum conditions in geometry are very important to determine. They typically are not found. Optimum geometry is not identified. Scaling studies should identify optimums. You will also find out that geometry is most important. Myths abound. Processing myths abound, right? Rarely challenged. Cause unnecessary constraints and can be dispelled. There's the old one, buy low, sell high. You really might want to change that to buy high and sell higher. And the question is CO2 a global warming gas? These are process myths that you're sort of stuck with, right? They're self-imposed processing constraints that are not necessary. They should have an origin. If you don't know where these came from, you should find out. If you can't find out the origin, then you should be careful. Let's talk about this one. Stock market, buy high, sell low, or buy low and sell high. So here's your stock price, and this is time. We have time marching on down here. So what happens is stock price is dropping down like that. And so you buy here. You buy it at the low point. You got the best bargain of the century. However, if it continues to go on down, then what was low is now relatively high to the present price. So you got to be careful about buying low because you may not be at the low. And basically, the first derivative, the slope, tells you which direction you're going. You have the information, and if it's pointing downward, it's likely to continue to go downward, right? Things have a habit of continuing to do what they did in the past, right? Continuing what they did in the past. Now, if we take a look at this, here's the stock price in the other direction. So you bought here. That's high. Oh, heavens. Oh, how ridiculous. You bought at the high point of the stock. However, over time, we put an E on the time down here, it'll continue to go up. So what was high is now low. So it's best to buy high and sell higher. Best to buy high and sell higher. Anyway, suggestion. Now let's talk about CO2 a little bit with global warming gas. You always see that being danced around. Just go camping. Just go camping. On a clear night, you're out there camping in your tent. So we have, there you go, here you in a tent, right? Everything's hunky-dory. And it's a clear night. And the stars are out. So you have stars out there. What happens on a clear night, it gets really cold. Now then, if you camp out on a cloudy night, so we have another camping trip here, and it's all cloudy up there. And here it was very, very cold. And here what happens is the Earth radiates to the clouds, and the clouds radiate back. So on a cloudy night, it's a lot warmer, just generally speaking. Right. So you got to ask yourself, why didn't the CO2 capture this and bounce it back to the Earth like the clouds do? That's because CO2 is only sorta a global warming gas. It's not nearly as powerful as water. Water is an extremely, in the form of clouds. Water is extremely warming, global warming. So, the truth of the matter, you should be monitoring cloud cover rather than CO2. CO2, you got to recognize a very simple thing about CO2. It's plant food. That's the other thing about CO2. It's being picked on. Everybody turns around and talks about CO2, how bad it is. Anyway, CO2 is actually plant food. The plants use it with sunlight, and they go through this process of photosynthesis, and they make carbohydrates out of it. So CO2 is not bad. I mean, CO2 is plant food. I mean, makes carbohydrates, so it's a good thing rather than a bad thing. It may come as an astonishment to you. What was really astonishing is the federal government declaring CO2 a pollutant when CO2 is plant food. Okay, I guess fertilizer or plant food is pollutant if it becomes excessive. So anyway, some of the things about process myths should question. And when they claim that the temperature of the Earth is rising, right? Global warming. You have all these people on television or in the news talking about global warming, but they never show you any data. They don't show you any data. And in truth, if you go into this area and study it a little bit, there's two sets of data. One set shows global warming, and you talk about how the measurements were made. And another set of data shows you global warming is not really happening. So you have two sets of data. The one that UAH is what it is. University of Alabama at Huntsville shows data where there is no global warming. And the NASA data, UAH is NASA, by the way, Huntsville, NASA, I think. Anyway, the other set of data is out of Cleveland, NASA, I think, up in Cleveland. It shows global warming. And I suspect just between the two of us, you and I, they're both right in their respective measurements. The NASA data tends to be taken around cities or high population areas. And I do think those areas are hotter than they used to be. When the sunlight is beating down on an open field and there's lots of grass and vegetation around, water gets evaporated. However, if you then take an asphalt jungle of a city here, right, and you hit it with sunlight, there's a lot of places where the sunlight is trapped. There is no evaporative nature of the sunlight in the city. So the global warming situation, two sets of data showing global warming and the other one showing not global warming. So it's a big debate. Anyway, I tend to think that global warming is a process myth myself, but I'm willing to also say that time will tell, actually. I'm certainly not an authority on, well, actually. Anyway, we'll just leave it at that. So the whole idea is self-imposed processing constraints is not a good idea. This is when I ran into professionally the Bingham plastic myth. The idea here is I have shear stress. This is the rheology data, and shear rate. And the data looks something like this. So the data went here. Now, all they did was project this line this way and claim there's a yield point. And that limited operations. However, the data actually went down this way, all the way down through here. And the difference between these, from the point of view of operating situation, is profound. Here it says processing essentially can be stopped. Here, the processing can go to completion. So the yield point myth seriously handicapped, well, not really, but seriously was in contradiction with actual plant experience. They never ran into a yield point in the plant. So you have this situation. I think this is radioactive sludge, and the sludge, only in famous tank 49 did the sludge have a yield point. In all other tanks, and there were 50 other tanks, there wasn't a yield point, at least as far as I understand the situation. So here's the Bingham plastic myth. Okay. Actually has false body 2 viscosity levels. The myth seems reasonable. Not true, caused undue constraints and prevented efficient operation. So, well, let me say it this way. It didn't really prevent efficient operation because the plant went ahead and ignored this myth and cleaned the sludge all the way to the wall, except for that famous tank 49, I think. So it didn't really affect operation. The plant just ignored it. And but however, it's a process myth that every so often I got an email about this. Saying I was wrong. Pretty funny. Myth 2, the importance of rheology. Ooh, I'm going to get into trouble here. Oftentimes, the detailed rheology is unimportant. Detailed rheology now. You hit the viscosity levels. Okay, you got the viscosity levels. You got the most important part. However, the detailed rheology, you don't need it. Now, having said that, I'll say that in some cases, rheology will control everything. So maybe 80% of the time, detailed rheology can be ignored. The other 10% of the time, or whatever, small amount of rheology, you need to pay attention to it. So you have things that are important until they aren't, things that are not important or not important until they are. Lack of time information. Very important. Time is usually not recorded. Processes have different time scales. Again, your kitchen sink you can turn off very quickly, but a huge pipeline that's 10 miles long, 10 feet a second going through there, you can't really operate that like your kitchen sink faucet. Yeah, lack of local flow behavior around the reaction zone. If the reaction is instantaneous, you need to record it as such. How long did it have to add the feed? At what level? How long did it take to fill the system? All kinds of questions. Times, okay? I was up visiting a pharmaceutical company. I was talking to the chemical engineer and the other people up there in the pilot plant area, and they said that all the reactions were slow, that the mixing was fairly unimportant. Then I talked to the lab chemists, and they said that the chemical reactions varied all over the place. Some were almost instantaneous and very fast, and some of them were very slow. Okay? Yeah. 2 different opinions, right? And same plants, same processes to observe 2 different ways. One said there wasn't any mixing effects on the reactions. The other one, other people said there was. It's not uncommon to have such conflicts. The question is trying to find a common ground. And so time scales, very interesting little item. Technical problems change with scale. Some disappear, other problems appear. Process sensitivity to size can occur. Large tanks, are very different than small tanks, period. Large plants, chemical plants, are quite different than small chemical plants. Procedural requirements. Unnecessary procedural requirements are scaled up. That's not a good idea. Procedural requirements have to be that there's a need for that particular procedure step. And you often see this as stir for 30 minutes or 8 hours. Add and stir for 30 minutes or 8 hours. Anyway, stirring for long periods of time, I don't know what that does, but, you ever notice people with their coffee, they continually stir their coffee? Processing time scales have long passed. It's a comfort factor, apparently. No importance to the process. No importance to the process. Local scaling and effects of heterogeneity. Multi-phase systems are often homogeneous. Spatial variations in properties occur. Specific local behavior may be important. And little information on local behavior. Neglecting simple processes. Low viscosity single-phase mixing is easy. You want to try to avoid problem processes. You want to try to avoid problem phases. And you really want to select the chemistry path that avoids multi-phase processing altogether. Lack of characterization of the process. This is very common. Right. Inadequate flow conditions, very common. Good pumping and circulation may not be occurring. You have formations of unmixed zones. Their adequate D over T ratio may be necessary. Remember, in the transition zone, you can have an impeller in there mixing away. Okay, and it's well mixed inside this cavern, but the rest of this is stagnant. Right. Assumed models, well, often a source of problems. White sticky solids, worst problems. Adhere easily to equipment, difficult to operate, clogged pipes, dewatering expensive. Dewatering and filtering are expensive. Materials change with scale. Oh, yeah. Change with scale. Material in the lab, not like in the pilot plant, not like in the plant. Shear dependent viscosities. One shear rate in the lab, one shear rate in the plant, and another viscosity shear rate in the lab, in the plant. So you have different viscosities in the lab, pilot plant, and plant. Moisture effects. Very important effects. Material history is also very important. Right. Inadequate characterization of geometry. Scale up by draftsperson is possible and can occur. This is not good. If you go in the area of atomization, they have a pre-filmer, right? Lays down a film of liquid. So what it looks like this. I'll change the color here. Ink color, go to red. So the feed comes in, fills this up in here with feed. Feed comes this way and overflows and forms a film, and then you have your drops being formed down here. Now the particular height in there, let me draw it again. Here's the step. Right. This in here, this particular region in here, is very important. Change it blue. This region right in here is very important. And literally the thickness of this film here determines drop size. And if you have something looking like this, let me go back to the red, I guess. If I have something like this, right, I'm going to, on the small scale, where there's not much height there, I'll produce a small drop size. When I scale up, I'll do a magnification of that, and maybe I'll have something looking like that. There's an awful lot of liquid now making larger drops. Anyway, the prefilmer, there's a very sensitive geometry measurement that needs to be kept constant on scale up if you're going to have the same drop size on scale up. But if the draftsman comes along and assumes geometric similarity and magnifies or enlarges that step in the feed, then he's changing the drop size, or he or she's changing the drop size. Another example might be a draft tube. So you have a tank in here, and then you have a draft tube in here at the bottom. This height in here, how far it sits off the bottom of the tank, becomes very important. All right, let's go in here, go over here. This height here is extremely important. How much the draft tube is causing this type of circulation. Okay, and this height down here that the draft tube sits off the bottom of the tank becomes an important geometry variable. Okay. By the way, draft tubes don't do anything except reduce variations, right? I don't. You sit there and wonder why you use draft tubes. Well, you usually don't, number one. However, in crystallization processes, you use draft tubes. Why? Is because they promote, they're growing crystals. And when you use a draft tube, you get more uniform crystal size than without the draft tube. So what the draft tube does is doesn't necessarily change mixing time or doesn't change mass transfer. What it changes is variations, reduces variations in performance, smooths things out. So that's what a draft tube does. Standard geometry, there's always better geometries. Non-standard geometries work better, right? Here's a case in point. You had a crystallization process. Looks something like this. And here you had a return line. So you had the crystals all up in here. And the return line. Now, they were returning a lot of large crystals, right? So what they did is, in this crystallization process, they put in a baffle. And the baffle was from right down here to there. So what then happened is the solid particles went around and went out. Whereas the very fine particles, the ones that are really tiny particles, they went down and around the baffle and went out here. So the big ones there's a size separation here, right? It's actually somewhat of a classifier. The larger particles sank, and the smaller particles were able to make the turn and go back to the crystallizer to grow more. Anyway. A standard retrofit in industry would be a well-placed baffle. Well-placed baffle. Major deviations between the pilot plant and plant exist. Unexpected plant results may occur. Repiloting may be warranted, and process performance can change. So you want to keep your pilot plant. I don't know if I brought that out or not. You always want to keep your pilot plant so you can do some testing or process improvements. Correlations, dimensionless groups, and correlations. Correlations are often not correct. Dimensionless groups are not complete. Correlations are incomplete, nonspecific. Mass transfer correlations. you're starting with very limited data. And the first one is Reynolds number, okay? Reynolds number is a fantastic number, but it can be very nondescriptive of the flow field. Very nondescriptive of the flow field. Equal Reynolds number does not mean same flow field. Equal Reynolds number does not mean same flow field. Very important point. Large diameter impeller at low speed has the same Reynolds number as a small diameter impeller at high speed. However, they're quite different in performance. Even though they have the same Reynolds number, the performance is quite different. And in mixing impeller pumping, there's got to be blade width effect. Here's blade width effect and blade number effect. This is the pumping number that ought to be used. It ought to take into account the number of blades and the width of the blades. Better definition of pumping number. Power number, the same thing. You should have a blade number in there, and there ought to be a blade width effect. D over T represents all kinds of effects, right? And it could be misleading as well. Dimensional analysis provides no help in interpreting this. You have to have some physical insight to do the interpretation. Adequacy of correlations. Well, right. So you have correlations based upon non-specific dimensionless groups like Reynolds number, right? No appreciation of complexity. Correlations leave the state of the process underspecified. Variable independence. Independency. Independence. Not all variables are totally independent. Changes in geometry are not necessarily independent. Most correlations are based upon boundary layer analogy. Agitated tank is very similar to a boundary layer. Processes behave as a boundary layer. Phenomena may follow that. Some don't. Right. Boundary layer shows an increase in transport with length. That's not true in an agitated tank. Energy source in agitated tank is fixed. Not so for a boundary layer. So there can be major difference between boundary layer and agitated tanks. And we haven't progressed that far yet. We're sort of like in a dark ages, right? You may think we're advanced. Yes, there's artificial intelligence. Yes, yes. They'll replace all the humans in the world with machines. But artificial intelligence only means there's going to be artificial stupidity or artificial mistakes. An example would be length, area, and volume dependencies not included. Mass transfer is a surface volume process. Volume in which the contacting is done should appear in the correlations. This characterizes the process. Doesn't occur. In such contacting, a contacting band often forms around the impeller. That's not included in. Right. Reference geometry should be perhaps in correlations. Scrutiny of correlation, we already mentioned that. I suspect that this is the exception rather than I suspect this is the rule. All right. You go to your boss, and here's the general correlation, and your data comes in like this. What's your boss going to tell you? Boss is going to tell you you're wrong, but not necessarily, because this happens all the time. Individual systems may not follow the general correlation. Example, case in point, I've already pointed this out. There are significant differences in behavior here. Scale of scrutiny for a correlation. At what level does a correlation hold? Correlation predicts variables over a wide range. Maybe don't predict variables over a short range. Other variables are acting as difficulties in piloting studies. If we go to correlations, if we take a look at this lead constant here, if you take a quick look, it goes from 0.3 to 0.74, factor 2 in this lead constant. The reason why that occurs is probably a reference geometry effect. Now, what's really cool about this, it's a very pretty graph, and it could be replaced by simply a table. The important item is right there. You have turbulent mixers going, probably turbulent, put it right in there. Turbulent mixers. And over here you have the transition regime. This is not the regime you want to use these impellers in. And up here you have the laminar regime. These are not the impellers of choice. This is a no-go. Although the data is there and it tempts you to use the impellers in this region, you shouldn't. This is the classic example of using a turbulent mixer in a laminar application. And really all you got to do is note that these are leveling off as constant values. The next thing you notice, they're independent of the Reynolds number. We already said that Reynolds number was questionable. Okay, sorry. And you notice that 1, 2, 3, 4, 5, and 6, how do they differ? Well, they differ by geometry. So even though the Reynolds number has horizontal lines, the Reynolds number has a little or no impact. You then turn around and see the importance of geometry poking through. All right. So, and case in point, don't use a turbulent impeller in a laminar application. Turbulent equipment will most likely fail in laminar applications. Remember the video that I showed you, G.I. Taylor, with his little boat, his two boats. One was powered by a spiral. It looked absolutely ridiculous, but it worked. The other one looked like a regular rudder. It failed, basically. So that's an example of turbulent mixer or turbulent equipment being used in a laminar application. It's a very serious design flaw, right? Lead constant, very important. A factor of 2, yeah. It may account for geometric and variable orientation, number ratios left out, undefined parameters, poorly defined dimensionless group, reference geometry, and a lot of undetermined effects. There's an awful lot of stuff that's buried in this K, right? This is gotten from theory. This is from theory. This is from experimentation. Anyway, this is heat transfer coefficient, function of Reynolds number, Prandtl number, D over T ratio. I'm not quite sure that's true. This is true for laminar flow. Anyway. Lead constant also will change with equipment. Here's an example for static mixers, 0.49 and 0.054 for agitated tanks. And I do believe down here we have this number, dimensionless group right here. This is a form of the OSOG number. Viscosity squared, generally speaking. and you have surface tension and density. And I think there's a length in there somewhere. What this number takes into account is differences in viscosity and includes the effect of surface tension. Effect of scale on data. Little data is taken at different sizes. Little data is taken at different sizes. So if you're going to scale up, you really need to close the gap there. Because your plant is over here, right, and your lab is here. You got to close the gap of information that sits there. Reference geometry is needed, perhaps. Processes do not overlap modest scales. The effects are real, and it's not due to poor experimentation. Little data is stained at different sizes. You need to fill that in. Apparent effects of correlations. The problem basically is you have no information. Scale is not taken into account. Correlations do not take scale into the account properly. Scale effects are due to size of equipment. Variety of correlations. There is a distinct lack of variety in correlations. Not as many scaling correlations as they may appear. Anyway. Analogies. Oh, I like analogies. They're a great idea. Great idea. Analogies are used everywhere. And they're very, very powerful. And I highly recommend the use of analogies. For example, the story, benzene ring looks like this. There's 6 sides to a benzene ring. And the chemist who discovered the structure of the benzene ring, he was dreaming one night and he saw snakes dancing around. And the snakes were dancing around. And they formed a benzene ring, or they formed this shape. When the chemist woke up, he had the benzene ring figured out. Basically, you can think of the ski lift being invented, and believe it or not, in Miami, Florida. And the idea is big bunches of bananas, not the bunches of bananas that you buy in the store, grocery store, but the big bunches of bananas. The chap who owned a ski resort in Idaho was watching how bananas were unloaded, these big bunches, coming off the boat from South America, Miami. He's watching it. And then he said, well, if they could do that with a big bunch of bananas, he can do that with a person down here that wants to go skiing. So put the skis on the person down here. Analogies. The other one, another analogy is, this one's attributed to Henry Ford. Well, maybe, maybe not. In the Chicago meat packing, or the slaughterhouses of Chicago, they would take a cow. All right, here's a cow. Feet there, tail, head. Guess we'll give it some horns. Okay, that's a cow. And basically they get steak, ground meat, whatever. So they would take apart the cow, right? First they probably hold it, hit it in the head, stun it, hang it up on a hook, maybe, then process it into different pieces of meat. And so as the cow went down the line, it became smaller and smaller and less recognizable as a cow and turned into steaks and whatnot. Henry Ford comes along and says, if they can do that with a cow that way, I can do this with car parts and build a car that way. So that's the idea of analogies between a car and a cow, is that cows and cars are both complicated systems, number one. They're also huge or relatively large systems, and they have parts to them. So you take it apart or put it together, One direction's taking it apart, the other direction's putting it together. And that's supposedly how Henry Ford came up with the idea of the automobile assembly line. All right. Bananas, cars, and cattle. And there was another one, a guy named Black and a guy named Decker was drinking whiskey Sunday afternoon. And don't know which way. There was a gun on the table. Black and Decker. And who knows who thought of it first, but that gun basically resembles an electric hand drill. So the basis of the electric hand drill was gotten by drawing an analogy to a pistol. So analogies are quite useful in understanding things, how things actually work. Useful when same physics occurs, useful for process understanding, useful in engineering. Okay, so free-flowing powders are like liquids. Continuous flow systems with large residence times are like batch systems. Heat's analogous to mass transfer. Agitated tanks analogous to boundary layer. Drops and bubbles are very similar to each other. And basically, analogies work very well. Analogies are not necessarily true. Free-flowing powders can demix. Jet mixing occurs in continuous flow systems. So, some analogies work and some analogies don't work. There's strange analogies. For example, their different systems can be very similar to each other. Bubble column, gas sparging and molten metal. The fish ponds and the metallurgist types, the people I run into, they get very angry when I tell them molten metal is just a liquid. But it is. But it's going to behave quite different than normal liquids like water because it has a very high, first off, it has a very high heat content. And second, it has a very high thermal conductivity, and it means that when it hits something, it will turn to a solid very quickly, unlike water. So there are similarities and there are differences. Molten metal is very similar to water, and then again, molten metal is not similar to water. So biological cells are very similar to liquid drops. The cell wall is similar to surface tension. Flux are similar to liquid drops. Electrostatic layers of flux are similar to surface tension. Okay, analogy is success and failure. The resemblance is high, yes. If the flow behavior is similar, yes. If the mechanism is similar, yes. So there's a level of scrutiny for analogies too. How close is the comparison going to be? What we have is the same physics, maybe with different equipment. Analogies are successful if they have the same physics or the same processing. Food analogies, there you go. Basically, a lot of your processing in the kitchen. So we have a kitchen sitting here, kitchen. The processing in the kitchen is very similar to the processing in your plant. So foods can be Newtonian, non-Newtonian, share process experience, common basis for foods analogies, lots of laughs. For example, paint pigment, mixing pigment into paint, you're going to have fish eyes. And fish eyes you also have in making pancake batter at home. So if you're having trouble mixing in the plant, you might want to try food experiments in the kitchen. So I recommend all people in the piloting area to begin to learn how to cook if you don't already know how to cook. I know how to cook. I got to eat. Anyway, learn how to cook. Good palating is very similar to good cooking. Heat transfer analogy. Well, heat transfer from a pipe is similar to heat transfer in an agitated tank. Analogy fails because you have a D over T ratio effect in the tank, but you don't have that in the pipe. Internals affect or interferes with the flow. That's also true. So there is no analogous D over T effect in heat transfer occurring into a pipe. Having said that, let me see if I can change that. What happens if I have a pipe and I add multiple numbers of small pipes in there? Now I may have a D over T effect. Analogies only partially hold. Now this one's kind of useful. And then some calculations, I misapply correlations, basically. Misapply correlations. There's fundamental reasons for why correlations occur. The Nusselt number is a function of Reynolds number. You can derive that from fluid mechanics. Number of revolutions to mix is volume divided by impeller pumping. Tank volume divided by impeller pumping. That's where the number of revolutions to mix comes from. And the atomization, we had pressure drop being the worker. So in atomization, you had mass flow rate divided by the pressure drop. So you could potentially understand the flow number, which is pressure drop divided by, mass flow rate divided by pressure drop, that flow number, and you apply it to other nozzles or other areas. What's interesting is, suppose the food company found a solution to a problem. Very excellent solution to a problem. That same problem also exists in the pharmaceutical industry and may also exist in the paint industry. So you turn around, you got a problem solved in the food industry, and suddenly it has more universal applications in pharmaceutical industry, and also maybe the paint industry. Anyway, so not only can we misapply correlations, we can also misapply correlations for the food industry into the paint industry, or the food industry into the pharmaceutical industry. Now then, we got to tell the truth here a little bit. Now, we were saying agitated tanks boundary layer. Okay, so what we'll do is we'll take the heat transfer correlation and remove everything. And we find out that, except length. We go into heat transfer correlation, remove everything except length. And you find out that the heat transfer coefficient goes up to d to 1/3 power. Okay. Now this is a very serious problem, actually. Now then, we do that for the mass transfer coefficient. Remove all the dimensions, all the variables, all the operating variables, all the fluid properties and everything. We reduce it down to simply how the mass transfer coefficient varies with length. Then we sit there and ask, are these simple effects reasonable? And unfortunately, the answer is a big fat no. So if I start changing my D over D ratio, as in scaling, I quickly find out we got bad news. In other words, at scale 1, everything's fine. But when I go up by a factor of 5, I got almost a 2%, a 1.7 increase in heat transfer coefficient. Going to a factor of 10, I get a factor of 2 in the heat transfer coefficient. I'm not quite sure that's realistic. It gets even worse in mass transfer. If I go up of a factor of 5 in mass transfer, I go up by a factor of 11 in mass transfer coefficients. That is not reasonable. So what I'm suggesting is that because we're doing boundary layer analogies and we're applying them to a agitated tank, that the information that we've gotten from boundary layer studies doesn't translate or does not apply to agitated tanks. And this is a serious challenge for us. And you can quickly demonstrate that with these types of simple calculations, right? So here you have the scale, and here you have what the heat transfer will do and what the mass transfer will do. So what this says is that this is highly improbable. No known mechanism to cause these phenomena. It's highly likely that the heat mass transfer coefficients will be less than that of the small scale, basically, or similar magnitude, not a factor of 2. Fortunately, scale change, 1,000, 100, or 1,000 in length, seldom encountered. Scale effects are present in correlations but not recognized. Examples of the breakdown of the boundary layer analogy occurs, right? A boundary layer analogy fails. If we go back to this, the mass transfer coefficient is notoriously has a reputation of being difficulty in scaling up, basically. And you can see why. You're getting unrealistic predictions. By using a regular boundary layer correlation, assuming it applies to an agitated tank, you're getting an unrealistic result. And you're anticipating this result to occur, factor 11? No. It probably won't go up by a factor 11. So you have the liquid mass transfer is notorious in scaling difficulties. And you can see why. So here is a very famous when I was in college, 1968 through 72. I guess it was around 1970. The lab people were working here, and they made the mistake of extrapolating up to this level, and they were anticipating production of 12, and indeed they got production of 1.2 maybe. So this is the idea of scale up being, first off, being an extrapolation. And second off, you can see that gas barged agitated control and gas band control, you have 3 different regimes sitting in here. Actually, this thing probably tips over and goes down. So what happens in the lab cannot necessarily be projected to happen in the plant. Serious difficulty. General conclusions. All right. Engineering, this is the conclusion of the entire course. I appreciate you lasting this long. It's tough. General engineering data tend to be faulty. Agitated tank is not a boundary layer. Sometimes it's fine to use boundary layer analogy. In other areas, not so much. Mistake in scale up occur. Inadequate dimensionless groups. Correlations don't specify the important phenomena. Unrealistic expectations occur. There are some things that are not scalable, right? Zeta potential, behavior, and Fodler design, just to name a few. Gas band, gas sparging, those things. Lots of changes that occur when you scale up. Doesn't mean you can't eventually be successful, but it's not going to be easy. Lots of technical mistakes occur. Pitfalls are waiting to be made. Scaling mistakes can be very costly. I.e., let's go back to this one right here. It was quite a disappointment. It's quite the rumor mill. See, you only learn this through the rumor mills, right? What people say by word of mouth. This is not written up, nor is it published in the newspaper, right? People don't like to publish their mistakes, right? Design is open-ended. You need to keep your options open, and there's no universal facility. Different designs, results for different processing, lots of different factors to be considered. Some processes are possible, others are not. Every process becomes a special case. This is very important right in here. Every process becomes a special case. You need continuing education. You need good communications. And I will emphasize by continuing education the comment I made about experts. All right. You have two experts, they're arguing. They're arguing. You could probably assume one of them was wrong or both of them was wrong. So what it indicates is perhaps you need to go study some more of your process. Listen to the experts and then realize that, well, maybe there's a lot more to it than what they're telling me. Anyway, I think that ends it. I hope you, thanks for coming. This course is usually given at some sort of hotel through various continuing education programs. But travel is often restricted, and people are not showing up to these as they used to. They think the business model is changing, so this is why the lecture series has been taped. Since you are already at home, I hope you're safe. It's very important. And of course, I'm open to a few questions all the time. I'm going to do a little blurb or a little video on stories, basically, is what I'm going to do. You can find it on my LinkedIn account, stories. There's an I here, ES. Stories. My email is always open. I am with the Chemical Engineering Program, we're no longer a department, at the North Carolina A&T State University. Telephone number? They haven't changed it yet. Anyway, that's my telephone number. Voicemail, do not leave voicemail. I don't respond to voicemail. Too many students call me up. You always want to try to reach me through my email account. And with that, I'm going to close this out, and I appreciate you participating all the way through this course. It's been tough, and I hope you are successful in your scale-up operations. Thank you very much, and have a good day.